Welcome back and hello everyone. Welcome to this chapter on thermodynamic potentials. And as usual, this is the summary of the things we're going to see. This is a rather long chapter, but it's compensated for shorter chapters later on. So, okay, what we're going to see is first of all, we are going to introduce what the natural and conjugate variables of the internal energy are. And this will allow us to derive what is known as the first Maxwell relation, and here using the same trick that we have just used in the entropy chapter of the applying Schwarz's theorem to a function of state as the energy. We can obtain like that a very non-trivial relationship between partial derivatives involving pressure, temperature, volume, but also entropy. So then we're going to define mathematically a new function of state. That's something we are going to call the Helmholtz free energy, and we're going to see that using the same trick of the mixed partial derivatives, we can obtain another very useful relationship that's called the third Maxwell relation. And then we're going to try to make it more systematic. So we're trying to find a way to define new interesting quantities from which to obtain nice relationships that we can then use when we're working in thermal physics. And this is a mathematical transformation that is called the Legendre transform. And by doing Legendre transforms on the internal energy, we are going to obtain two further interesting functions of state, the enthalpy and the Gibbs free energy. And from each of these new functions of state, we are going to obtain one relationship, which is going to be important later. Okay, so then we are going to talk again mathematically about something we are going to be doing often in this course, which is the reduction of derivatives. So often when we are studying a problem in thermodynamics, we have to ask ourselves about some partial derivative of something which is maybe not experimentally accessible. For instance, the internal energy, or for instance, the entropy. Okay, and there is a systematic way to turn such partial derivatives into experimentally friendly expressions that depend only on measurable coefficients, such as the coefficient of thermal expansion, the isothermal compressibility, and the heat capacities, and also pressure, temperature, and volume, but none of the complicated objects like entropy or internal energy that we cannot just go and measure on a system. Okay, so I will illustrate in an example this reduction of derivatives in the synchronous session, and in the problem sheets of this week there are going to be a lot of this reduction of derivatives, because practice makes perfect, so it's important to practice these things. Then I'm going to introduce similar quantities, new functions of state, which instead of being obtained from the internal energy are obtained from the entropy, and these are called entropic potentials. And we are going to learn about the free entropies, which are those entropic potentials, two of them. And to close the chapter, because I don't want to leave it so mathematical, I want to try to connect these mathematical definitions to physics. So in which situations does it make sense to think about the Helmholtz free energy, or the Gibbs potential, or the enthalpy? Okay, so we are going to look specifically to isothermal processes, or rather processes in contact with a heat source. That's when the Helmholtz free energy F becomes important. And we are going to obtain a very important result, which is the minimum F principle, the minimum free energy principle. Then, considering isothermal and isobaric processes, we are then going to obtain the minimum Gibbs free energy principle. And this minimization of these new properties of state, singling out stable configurations of your system, is what justifies that we call those properties of state potentials, because you minimize them and you find stable state of your system. To talk about enthalpy, we are actually going to study a historical experiment. And this is the Joule-Thomson experiment, or the throttling experiment, also called the Joule-Kelvin experiment or the porous plug experiment. They're all the same thing. And in this experiment, the enthalpy is a constant in the process. So that will allow us to give some meaning to the concept of enthalpy. And revisiting this historical experiment is yet another attempt of Joule to experimentally demonstrate that the ideal gas has an internal energy that depends only on temperature. So we're going to learn about that as well.